Hey everyone, and welcome to The Explainer. Today, we are setting the stage for a seriously cinematic clash of foundational computer science algorithms. If you've ever wondered how data actually goes from a totally chaotic mess to perfect order, well, you are absolutely in the right place. We're going to break down the mechanics, the code, and the real-world performance of three absolute classics. Get ready for the ultimate sorting showdown.
Okay, so picture this. Someone hands you a list of 100,000 completely random numbers. Finding the maximum value? Sure, that might take a moment. But arranging every single one of them from smallest to largest? Now that is a chaotic problem. Whether it's organizing your playlist, ranking search results, or, processing millions of financial transactions, sorting efficiently is a massive real-world need that computers face every single second of the day.
All right, here's our fast-paced game plan for today. 1. The sorting problem. 2. Bubble sort. 3. Selection sort. 4. Insertion sort. 5. Complexity, stability, and showdown. And 6. Interviews and real applications. Let's get right into it.
Starting off with Section 1, the sorting problem. Before we jump into the solutions, let's just clearly define what we're actually trying to pull off here.
At its core, sorting is incredibly simple to grasp. The ultimate goal is just to arrange an array so that the element at index 0 is less than or equal to the element at index 1, which is less than or equal to index 2, and so on, all the way down to the end of the list. Look, whether we are dealing with basic integers or super complex employee records, we just want everything sitting there in perfectly ascending order.
And that brings us right to our first contender. Section 2. Bubble sort, also known for its signature bubbling up action.
So, bubble sort actually gets its name from a very physical visual. Imagine air bubbles rising to the surface of a pool, or picture a line of baseball players trying to organize themselves by height. If you're standing next to a player who's taller than you just swap places. That's it. The algorithm literally pushes the largest, heaviest elements to the far right end of the array, while the smaller elements slowly kind of bubble their way up to the front. Let's do a quick dry run to see this in action. Step 1. We start at the beginning of the array and compare the first adjacent pair of elements. Step 2. If the first is greater than the second, we swap them. Then, we move one position to the right and repeat. Now, by the time we hit the end of the array for the very first time, Step 3 guarantees that the absolute largest element has bubbled all the way to the very end. It is now locked into its final correct position. Then, Step 4, we just repeat this entire process for the remaining unsorted portion of the list.
If we peek under the hood at the Java code, it's driven by two loops. Your outer loop runs n times to make sure every single element gets sorted. The inner loop is doing the actual heavy lifting, comparing adjacent items and swapping them. But check out this brilliant little optimization. If we add a simple Boolean flag called swapped, we can keep track of whether any swaps were actually made during a pass. If we go through the whole array and swap absolutely nothing, boom, the array is already sorted, and we can just break out early.
All right, moving on to our next contender. Section 3, Selection Sort, or what I like to call the smallest first approach.
Now, while bubble sort focuses on pushing the largest items to the right, selection sort does the exact opposite. It actively hunts down the absolute smallest element in the entire unsorted portion of the array. Once it finds that minimum value, it grabs it and directly exchanges it with the element sitting in the first available position on the left.
Here is the dry run for selection sort. We start by scanning the entire array for one reason: to find the absolute smallest number. We grab it and we exchange it with whatever happens to be sitting at index 0. Great! Index 0 is now permanently sorted. Next, we scan the remaining unsorted part of the array, find the second smallest number, and exchange it with index 1. You can really see here that selection sort spends the vast majority of its time just frantically searching for that minimum value.
The logic for this one is pretty elegant, actually. Your outer loop tracks the current position you're trying to fill. You start by just assuming the current index is your minimum. Then your inner loop races ahead, checking to see if any subsequent elements are smaller. If it finds one, it updates the minimum index. But notice the huge difference from bubble sort here. Selection sort only performs a single swap per outer loop iteration. It's not constantly swapping adjacent pairs all the way down the line.
Time for algorithm number 3, which is often the favorite for smaller tasks. Section 4, Insertion Sort, famously known as the card player's approach.
Seriously, if you have ever sorted a hand of playing cards, you instinctively already know insertion sort. Think about it. You hold the sorted cards in your left hand,
You pick up a new, unsorted card with your right hand, compare it to the cards in your left, and slot it exactly where it belongs. You're building the sorted array one element at a time, perfectly preserving the relative order as you go.
Visually, this step-by-step dry run is super satisfying. We start by just assuming the first element is already sorted. We look at the second element, and if it's smaller, we swap. Simple. Then we grab the third element. We scan backward through our little sorted section, shifting any larger elements to the right to make a perfect little gap. And finally, we just drop our new element right into that gap.
Looking at the Java implementation, the key detail that makes this tick is the inner loop. The outer loop grabs the next item and stashes it in a temporary variable. But that inner loop, it actually scans backward, which you can see with the JJ. And crucially, it stops the exact moment it finds an element that is smaller than our temporary variable. It doesn't waste time checking the rest of the array because it already knows everything to the left is perfectly sorted.
All right, it's time to take these 3 theories and throw them into a real-world arena. Welcome to Section 5, Complexity, Stability, and the Final Showdown.
Let's talk big O notation. First, the good news. All 3 algorithms have a space complexity of O of 1. This means they are in-place sorts. They don't hog huge amounts of extra memory to get the job done. But look at that time complexity. In the worst-case scenario, like if the array is completely backward, they all suffer a really painful ON squared time. However, if the array is already mostly sorted, bubble sort and insertion sort can tear through it in a blistering ON time. Selection sort, sadly, is stuck at ON squared even on its best day. Why? Because it mindlessly searches the entire array anyway.
And wow, this brilliantly illustrates the real-world impact of that math. This is actual benchmarking data from an IRJET study sorting 100,000 elements. Check out Insertion Sort handling a fully sorted array. 0 seconds. It literally instantly realizes the job is done. Meanwhile, Selection Sort wastes 10.2 seconds checking an already sorted list. Ouch. But to be totally fair to Selection Sort, when the data is completely unsorted, it actually beats Insertion Sort, clocking in at 9.6 seconds versus 12.4 seconds. So the real deciding factor often comes down to this one crucial concept: stability. Stability simply means retaining secondary ordering. Imagine you have a database of employees already sorted alphabetically by last name, and you run a new sort by zip code. A stable algorithm guarantees that employees with the same zip code will safely remain in their alphabetical order. Bubble sort and insertion sort, highly stable. Selection sort, because of how it wildly leaps across the array swapping elements, it is notoriously unstable.
Let's wrap the whole thing up with Section 6, Interviews and Real Applications. Basically, what do you actually need to take away from all of this?
Okay, here are your actionable rules of thumb for acing that next technical interview. Bubble sort is largely educational, though that optimized O-event best case makes it a quick way to check if data is already sorted. Selection sort is great when memory writes are super expensive, simply because it only swaps once per iteration. Insertion sort is actually heavily used out in the wild as a hybrid component in much larger advanced algorithms because it is just lightning fast for very small data sets or arrays that are already mostly sorted. And of course, remember, all 3 save you precious memory with that O1 space complexity.
You did it. You've just conquered the foundational sorting algorithms. You know exactly how they think, how they perform, and where they actually thrive. But listen, the world of computer science definitely does not stop here. The big question is, now that you've mastered the basics, are you ready to explore the blazingly fast worlds of merge sort and quicksort? Keep learning, keep optimizing, and I'll see you in the next explainer.